want to know what we want in the assignment. This applies to both of them as well. With anything to do with grading criteria, what we can do is we can sit down and we can say, do this, followed by do this, followed by do this, followed by do this. You get a series of tick boxes, you get 100%, you're very happy. I'm not very happy because the external examiner goes mad at me and says, but you haven't left enough scope, so the ones who are high flyers can do better than those who are slightly less high flyers. So we need something that we can discriminate against people that really do have an in-depth understanding and people who have a slightly more superficial understanding. So there will always be a certain amount of discretion in the marking. Always. And you always find this at degree level. And it's a subject of some consternation for students because students want an exact breakdown. Where does this 1 mark come from? Where does this 1 mark come from? And I make absolutely no apologies for not going down that route at all. However, what we can do is we can define some pretty concrete things that I would expect to see in there. So if we go around to the board here, so we've got standard engineering, and this is electronics, so it is engineering. Your standard kind of engineering document is generally going to have the form like you would write a technical paper. So that would be abstract, introduction, main body. Now don't call it main body because someone did last year. That's not what I mean by the main body. Now your main body could consist of a number of subsections, which might be introduction to photocopiers, operation of supercapacitors, this kind of stuff. It could have several different sections in that main body, followed by conclusions, followed by references, followed by appendices. Okay, that's the general form. That doesn't tell you a great deal about what the report is, that just tells you, you know, like how to deliver a letter, you've got an address on the front and so on. That's the kind of hard rules. Maximum I want is 8 pages, including diagrams, so you need to be concise. I don't want to sit down and read 30 reports, despite the fact I know they're wonderful. I don't want to sit down and read 30 reports that are 50 pages long because you think by including 50 pages I'm going to be impressed. Probably quite the opposite actually, because if someone does do it in less than 8 pages and it's very tight, neat and concise, and go straight for the details that we're looking for example, on the photocopper, it'll be the charging curve, right? That's important. It will be the discharging curve. It will be identification of the time constants. If you don't know what they are, you need to ask myself and Mike to explain them to you. It's going to be the operation itself. What was hard? What was easy? Where you would go to improve it in the future. What's a good photocopper? What's a bad photocopper? You're doing these experiments, and you should be able to convey to someone else who hasn't done these experiments what your experience was. That's what the report is all about. It's about what you learned along the way and where you got the basic information from. Well, you've got the references, probably find a few more, that might impress me. Of course, you know referencing and citation, or you should do at MSc. So down the bottom you have your square bracket with 5 or Smith or however you want to do it, but with your square bracket at the bottom, followed by the full reference, which would be even down to page numbers, and then you might in the introduction say, photocoppers were first introduced in 1975 by Smith, square bracket, and that's the kind of thing you would do in there. So you would establish the fact in the report that you were well read in what you were doing. To just do something mechanically, the big guy in the lab with the big hair said, build me X, Y, Z, so I built it, here it is, and it works. That's not good. But what is good is, this report documents the operation of a photocopper. Not even the context. It doesn't even need to be inside the context of 721. Imagine it's not. Imagine you're just writing a paper for someone to try and understand what a photocopper is, how it works, what the shortcomings of it are, why we do it in the first place. What is it? What is it? How does it work? Why does it work in this particular way? And so on. Okay, so your basic format, abstract introduction, main body, conclusions, references, and appendices, okay? So that's your format. Now we come down to the kind of breakdown that I know students like so much. This is where you get your marks from. Now, I'm not trying to steal marks away from you, although that accusation is quite often made. I'm not trying to take marks away, I'm trying to give you marks. But if there is something quite obviously missing, you can't have those marks. So for example, circuit diagram, 5%. Do you get 5% just because you've got a circuit diagram? No. You get that 5% if you've got a circuit diagram that looks nice. Now you see where the discretion's starting to come in. References, citations. If you just include the 2 references I gave you, you're only going to get probably half the marks, because I would expect you to do a little bit more reading outside of that, even if it's only 5 minutes on a Google search. PCB layout, 10%. Now this is where I've really got you, if you see what I mean, if I'm the big evil person that steals your marks, because there will be some very, very good solutions. Usually they're about that kind of size, and there will be some very bad solutions that are usually about this kind of size. So, size of the board is important, layout of the board is important, even just down to the shape of the board, etc. Okay, so there's a lot of discretion attached to the layout. Publicity, or just couldn't think of anything else to call it, but the way in which you present it. So this is a very visual thing. These are exciting things. You've got robots wandering about and everything. Let me see some photographs of it. How good are the photographs? Which angles are you looking at? How you explain the fact that it moves? All these kind of things. So some kind of graphic contained inside there. Explanation of operation is another one that I've got you on, because you could just go into the references and pretty much put that in your own words and claim that as your own references, which I know a lot of people do. You can't put the same text in, but you can paraphrase it if you like. But there's a risk attached to that, because is it you understanding it, or is it the reference understanding it? Well, obviously it's the latter, and that will come across in the text. Whereas someone says to me, well, actually what's going on here is I'm using flashing LED, and what's happening with the flashing LED is at a threshold. So when the capacitor charges up beyond 2.7 volts or whatever the threshold is, that causes the base of the BJT transistor to go into forward bias, therefore conducting current through the motor. You see how easy that was? 2-3 sentences. That would be all you need for the explanation. But I can do it because I've got some understanding of it. That's what I'm trying to encourage you to do. Put it in a nutshell. The important, the key things, rather than a big long bit of text, which rather demonstrates poor understanding. Evidence of measurements. So let's have a look on the board on the kind of measurements I would expect to be in the report. So one of the primary things, remember, because we just had this kind of operation, didn't we? So we had a capacitor, and we had a switch, remember, and this was what we said our photocopper was essentially like, didn't we? Okay, and off here, of course, we have our solar. I'll just represent that. Not sure what the symbol is for solar, actually. Or is it right? Similar to that, isn't it?
Looks good to me.
Yeah,
with some arrows pointing into it.
Not sure what the is it? So that's the IET form for solar power. Yeah, anyway. So that's the basic essence of it, and this is your clever circuit which is doing the automatic switching, right? Yeah. All agreed? So as this panel begins to charge up, or as the panel begins to charge the capacitor, can that panel supply infinite current? Very easy question to start with. Yes, no? Nod your heads or shake your heads accordingly. Can it supply infinite current? No. Fantastic. So it means that the current that flows down here is finite. In other words, it's smaller than the universe or whatever you want. So what restricts it? Well, what restricts it is the surface area and the silicon which is contained in it. And of course the amount of light falling on it. So what that means is this is a storage capacitor. So a storage capacitor is nothing more than really a bath. And here's the tap on the top of the bath. And here's the water going into the bath. Obviously the bigger the tap, or the more I turn the tap on, the quicker the bath fills up, right? So that's what happens to your capacitor. So the more light it gets, going back to the proper one now, so the more light that we get on here, the faster that capacitor is going to charge up. So what that's going to look like is in low light, you're going to get a curve that looks like this. In medium light, you're probably going to get something that looks a bit more like this. And in high illumination conditions, something like that. So you've got three different curves there. I'd like to see some kind of indication as to how long this is. How long does it take to charge up that capacitor? We can do that from direct measurement. Just put a voltmeter across the capacitor and measure it. You can see it going up on the oscilloscope. That's the kind of thing that I'm looking for evidence of measurements. So some kind of indication of that, possibly even that this point here and this point here, so this is your V max, the maximum voltage the cell can provide, some kind of indication that you might even understand time constants. In other words, at that point there would be 5 tau, but I'll let you do some stuff on charging and discharging curves for yourself on that. So evidence of measurement, justification for choice of circuit. So why did you choose the photocopier? Because it was easy. Fair enough. Because you liked it, because it had the possibility of injecting light from outside. That might be another good argument for it. Why did you choose